In this video, we're going to be learning about the COMSOL environment, where we will be doing all of our finite element analysis in this course. So it's better to start with learning about the environment first before we jump into the more advanced analyses. So when you start COMSOL by double-clicking on the icon on your desktop or finding it from the start or the application menu, you're greeted with this window, which is the blank window, and it has a few options available. Well, it says new because I just started the program, and it gives me an option for model wizard and blank model. If I click on model wizard, it will take me into step-by-step model definition process, basically the dimensions, the physics, the study, and all of that. If I click on blank model, it will take me into a blank COMSOL window where I have to add everything manually, like the physics or the study and everything else. I can cancel this, which I don't know what it would do because I just opened the window, and I can look at help. So what I'm going to do is click on the model wizard, and the first option is to determine the dimensions of my model. Is it a 0D, like a point analysis, 1D, which would be lines appropriate for beam and truss analysis and statics, 1D axisymmetric, which if you have a 2D model but it has a symmetry about an axis. We have a 2D analysis like plane stress and plane strains, then 2D about a symmetrical axis, which gives you a 3D but like more simplified analysis. Then we have a 3D analysis, which has like probably the more complicated analysis. So for this introductory example, I'm going to click on 3D. What I want to do in this example is just to create a little cube or bar, fix one end and apply some tensile force on the other end and see the stresses in there. So I click on 3D, and then I go to the next window, which is select physics. In this window, what we're doing basically is telling COMSOL what kind of equations or governing equations we want to solve. And the options you see on your COMSOL would be different from mine, depending on the modules you have available to you and you've purchased. Here I've purchased these modules, and I have the AC/DC, acoustics, chemical, fluid flow, heat transfer, structural mechanics, and mathematics. And each of these, as I said, refer to a certain governing equations that you want to solve in your model. So for example, if I click on acoustics, there's some information on the left or the right panel that tells me what this physics do. And I can click on the arrow right next to it, and I can see the sub-modules I have available on my program to deal with. So like pressure acoustics, thermoviscous acoustics, air acoustics, the stuff that I have available to me. If I click on heat transfer, I can see the modules or the sub-modules available with the heat transfer module. And I can click on structural mechanics, and I can see the sub-modules available with my structural mechanics module. When you click on each of these sub-modules, again, you see a text on the right panel that tells you what kind of analysis you can do with that sub-module. So solid mechanics, the shells determine that, beams and trusses, all of these will show you, or will show up over here, tell you what you can do with that sub-module. This is very helpful. So you don't need to open a help window and read through it. This is a very detailed and short and to the point explanation of what you can do with that selected sub-module. So once you click the one that you want, you can either click add or double click on that sub-module, and that will be added to the added physics interface. And you can add as many physics as necessary based on your analysis and couple them so you can have a, as is written over here, a multi-physics problem. So you can, for example, couple the structural mechanics with the heat transfer analysis and have a coupled simulation between structural mechanics and heat transfer. And once you click on each of the physics on the added physics interface, you can see on the right panel the degrees of freedom that will be solved with that physics. For example, here in the structural mechanics, I have displacement field, or I can say this is vector shown by u, and then the components of that displacement field, which are u in the x direction, v is the displacement in the y direction, and w is the displacement in the z direction. So again, if I needed to add more physics, I could just double click on them. But right now, again, this is a very simplified analysis, so I'm not going to go into the advanced example. So I'm going to click study. And here, I'm given the option to pick what kind of study I want to do for my analysis. There are 4 general studies that are commonly used. Eigenfrequency, which is for modal analysis, finding the natural frequencies and mode shapes of some objects. Frequency domain is for harmonically or harmonic excitation, so you can get the frequency response for the excitations of an object. Stationary, which is the easiest case when you neglect the mass and damping, basically, for most cases. So it's kx is equal to f, basically. That's what it does. And it's appropriate for steady state analyses. And then we have time dependent simulation. In this case, for time dependent, either the forces or material properties or both, or maybe even more parameters change over time, whereas in a stationary analysis, nothing changes over time, as is written on the first sentence on the explanation on the right panel. We can also have some specific analysis. For example, here we have eigenfrequency pre-stressed, which is appropriate if you want to, for example, find the mode shapes of a drum head after you have given it initial stresses. And again, so you can go through all of these steps or study types and read on the right panel what each one determines or correspond to. And if I click on the eigenfrequency and pre-stress, it tells me that the pre-stress analysis eigenfrequency study is used to compute eigenfrequencies and eigenmodes that are influenced by a prior static load. So for example, in that drum head analysis that I was talking about, you can create or design a drum head and then give it initial stresses, run a static analysis first to determine the stresses inside it, and then those stresses will determine the stiffness of the drum head, and then you can run a eigenfrequency analysis to find the mode shapes and natural frequencies. But for this example, I'm going to go with stationary or steady state, and I'm going to click done. And after a couple of seconds, I am taken into the main window and COMSOL. So this is where everything happens. All the steps in your FEA analysis and COMSOL happens on this window. It has a few panels. I'm going to go through them briefly and give a little example of how we can do FEA analysis in COMSOL. We have a model builder panel where it has a lot of options and tree view options. These options, some of them are the same for every kind of simulation you want to do. And some of the options, like for example, the study or solid mechanics step will be different, because in this case, I'm doing a solid mechanics. In a different case, I might be doing acoustics or heat transfer or coupled physics. And based on that, some of the features on the model builder will be different. But the global definitions, the geometry, materials, meshing, and study, they will be the same for any kind of simulation you want to do. And if you look at the middle panel, it changes as I click on different options on the left panel. So in the middle panel, we are given the opportunity to set some of the options and features. For example, boundary conditions, forces, information about the meshing, or dimensions in the geometry, or defining parameters, for example, in the middle panel. So the middle panel is where we define values for some of the options of the features for each of these the features or options on the left panel. So for example, if I click on geometry 1, two of the things that are interesting is unit length. So you can set your numbers to be by default in microns or micro inches or nanometers, or you can work with meters, kilometers, miles, and all that. And COMSOL gives you the opportunity to work either in SI units or English units. I'm going to keep the unit length in meters, and then I have the option to change the units for angles, and degrees and radians are the two options I have, and degrees are easier for human brain to comprehend, so I'm going to keep that as degrees. In the right panel, I have two windows. Let me expand a little bit. I have this window with options similar to what you see in any CAD program like SolidWorks. We can zoom in, you can select stuff, you can make wireframe or transparency, you can look at 2D and 3D views, and again zoom and zoom out and zoom to extent or zoom box. You can take pictures of your window, you can print it, and you can do a quick snapshot as well. And once you start a simulation, all the information will be shown on the bottom window in this right panel. The progress, if it's a lengthy simulation, you can see how far your simulation has been going on. The log part gives you a detailed information about the convergence, about where it is in terms of the error and tolerance. And the messages, for example, if you open something or save something, or there is a message that COMSOL wants to show you, it will all happen on here. There will be more tabs as you run a simulation and you want to show some numerical results. It will all show in terms of tables in here. As we do, we will see those happen. Then we have a ribbon on top with some tabs. Each one has its own features, options, and commands, which is not efficient if I want to go through each one individually right now. As we do examples in this course, you will become familiar with the options that each of these commands or buttons give you. So I'm not going to go through each of these right now. Again, you will see them as we work on examples. So like I said, there is an option to define parameters. You don't have to do this, but it would save time if you're running an optimization model, or if you want to run some analysis for a similar geometry but with different dimensions. You can define the geometric parameters over here with names and values, and you can do a parametric sweep analysis in COMSOL, which makes life a lot easier and more automated. For the sake of showing you how parametric simulation happens, and or you can define parameters even if you're not doing parametric simulation in COMSOL, I'm going to go define 3 parameters for my model, which is going to be a simple block. But again, I'm going to do it here just so you see how it works. I have 4 columns. One of them is gray, so I cannot change this middle column. But I can give a name, an expression, and then a description for each of the parameters. For example, I'm going to give one parameter called L, and the expression for that is 1 meters. As you can see, I can define the unit of my expression and in between some brackets. And when I press tab or enter, COMSOL determines that the value is 1 meter. And if I want to be make sure that when I come back to this model, say 1 year, 2 years, 5 years later, and I want to go through this, in order to prevent forgetting what each one of these parameters mean, I can define I can give a description. For example, bar length is for the first one, and then I can say let's say W, and I want to give it, say, 10 centimeters. So I can do 2 things. I can say 10 and then open the brackets and put cm for centimeters and close the bracket. And if I press enter, COMSOL will know that it's 0.1 meters, and it puts the meters because that was a default unit we picked for length and the geometry. So I defined 2 parameters, L and W. So what I want to do basically is going to create a bar with a square cross section. So let's call this bar width. So I have that one also determined. So I'm going to use these 2 parameters to create a a bar with a square cross section. Also, what I could do if I didn't want to give in centimeters, right? The other option I had was to type this 0.1 meters, and that would do the same thing as before. But in order to show you that you can mess with the units or be flexible with the units, I'm going to do it like this: 10 centimeters, press enter, and COMSOL already knows it's 0.1 meters. So I created two parameters. Now let's go ahead in the geometry and create a block with those two parameters. So when you come here, you can click on the geometry tab on the ribbon up top, and you have options over here. If you want to start from a 2D model or sketch and then do extrusion or revolve, you can do that there too, and we will do in the upcoming examples. But here what I want to do is basically create a block. So I click on a block. I also could create a sphere. All of these options are available, and you can just play with that and see what each one does. So let's create a block. When I click on that, under the geometry tab or option over here, I have a block, and it requires some information. So it's asking me to determine the width, depth, and height of my block, as well as where it's positioned, position of the center point or the position of the corner point. So I can give these values. Let's see what happens if I just leave values or numbers. And you see that I have a block 1 meters in each direction, or 1 meter in each direction. It's the length. And the corner point, which is the bottom left corner, is located at 0, 0, 0. If I change this to center for the position and say build selected and zoom all, this is the button for zoom all, you see that now the center point of this circle or the block is at 0.000. So each of the corners at this corner is at minus 0.5, minus 0.5, minus 0.5. And I can change these values if I need. So I can make this one 10 meters in width and do the block and then zoom all, and this is the block like that. But what I want to do is, instead of giving these values, I want to use the parameters are defined over here. So I'm going to give L for the length, and I want to put W for both width and depth. So W and L. If I click on that and zoom all, this is the bar, and now you can see that the bottom face is 1 by 1 or 0.1 by 0.1 meters, and the length is 1 meter. And one thing else I want to do in the 3D view to make it easier for my eyes is to turn off this orthographic projection, so it's easier for my eyes. The other thing I want to do, or I want to play with, or I can, is to change where it is. So I can, right now the center point of this block is at 0, 0, 0. I can change it to the corner point to be at 0, 0, 0, and then zoom all. So now if I do a 3D view, this corner is at 0, 0, 0. It doesn't matter really, unless you're doing a complicated geometry, then you need to know where every object is located. So I'm gonna keep the center or the corner at minus 0.5 and Y at minus 0.5 and Z at 0. So if I do that, it's just shifted a little bit. So see what happens. So if I look at the XY direction, minus 0.5 to 0.5, and then I have minus point, probably this is not showing right, but that's where it is located. I won't lose sleep over that. So, or one thing else you can do is say instead of doing that, you can say, I think I gave it wrong. So that was my problem. I should say minus w over 2 because that's 0.1 divided by 2 is 0.05, not 0.5. So if I do this, it would make it better. Now zoom all. And if I look from the XY direction, this is correct. My mistake was that I missed this 0. So now the bottom corner here is at minus 0.05, minus 0.05, and 0. That means the center, this here, is at 0, 0, 0, the center of the bottom face. But that's not really important. That's just me being nitty-gritty right here. Unless you really you want to add something to this and extrude and cut, extrude, and everything else, which I'm not doing in this example. So that's not really as important in this example. So once done, click on the geometry and say build all, and that's done. The next step is to define the parameter or the materials, sorry. So in the materials, you can right click here and say add materials from library. And then there's a built-in materials, and then also there are some physics dependent materials, for example in MEMS or piezoelectric or liquid and gas. So I'm gonna stick with the built-in, and I want to click steel. And once it's done, I can look at the material properties right here. So the ones which have this checkbox on the left column are the ones that are used for this specific analysis. For the case of a solid mechanics steady state, I don't need to use relative permeability because I don't have any radiation or fluid flow through it, heat capacity, and everything else. So if I were having a coupled physics analysis, some of them would probably be checked and used in the analysis. So COMSOL has some predefined values which you can use, but if you want, you can change them. For example, for the Poisson ratio, I can change it to 0.3 if I wanted to, or I can change it back to 0.28 if I needed to change those values. So the values are given, the default values, but it's not like you cannot change them. You can change them as needed. So if you paid attention, before I clicked on the materials, there was a red cross on the materials thing because COMSOL hadn't registered that I have defined the material. But once you do it and you select materials again, as long as there is no domain in your analysis which doesn't have a material attached or defined for it, there will be a cross mark. But once you do that, there won't be a cross mark on the materials tab. Now that we're done with our simple model creation, this is the solid model creation, what I can do is to define the boundary conditions and the loads. In this example, I want to fix this end, the bottom end, and I want to apply some tensile force on this surface. So I can click on the solid mechanics tab and right click in this, and I can see a bunch of options available to me. And one thing you can probably observe in COMSOL is that the types of boundary conditions and forces are categorized in terms of being that for the domain, being that for the boundaries or the edges or the points, right? So in COMSOL, points are called edges, or no, sorry, points are called points, the lines are called edges, the surfaces are called boundaries, and the 3D thing is called the domain. And you can also see that over here, you have domain, boundary, edge, and point, and you can select an object, right? So in this case, this is a 3D model, this is a domain, but I want to apply the fixed boundary condition on this surface, and I want to apply a tensile force on this surface. So I'm talking about surfaces, so I'm going to look at the boundary loads and fixed constraints on the boundaries. So when you see a icon like this next to an option or a force or boundary condition, that means on a boundary. So let's apply the fixed constraint first. I click that, and now here it's telling me, okay, which surface you want to add the fixed constraint. So I can rotate this with the left click of a mouse and dragging, and then once you see this is changing into red, I can select that, and that surface is selected and shown in the selection window. So what this means, if I click on the equations, is that all the displacement of the points on this surface are equal to 0. And since this is in bold, this is basically in vectors. So ux, uy, or uz, or u, v, w, if you remember from that window, are equal to 0. So none of the points on this surface are going to move anywhere. Then I want to apply a tensile force on this surface. So again, right click on the solid mechanics. Now I want to select boundary load. The boundary load, first thing I need to determine which face. So I'm going to say apply a boundary force on this face. Again, when it's red, it's ready to be selected. Then what kind of force I want to give, right? Force per unit area, pressure, or total force. For force per unit area, I'm able to give it in the X, Y, and Z direction. For the pressure, I can only give one value, Pascal, which is newtons per meter squared. Again, if I look at the force per unit area, newtons per meter squared or pound per inch squared, right, PSI, would be the same thing as pressure. And pressure is always normal to the surface. So there is no other direction you can give for a pressure for a given surface. I'm going to give it as pressure. And one thing to remember is a positive pressure is basically going to be compressing this bar. And negative pressure is going to be acting as a tensile force. So I'm going to give a minus, let's say, 100 Pascal pressure on the surface. And if I press enter, that's done. So what I get here is a bar that it was basically simply modeled 1 meter in length and 0.1 meters in the surface cross-section area. Applied a fixed boundary condition on this surface and a tensile force on this surface. The next step is to mesh this model and then run an analysis. So because I don't want to make this video too long, I'm not going to go a lot into how to mesh things, but COMSOL has this feature here that gives you some easy meshing step. You can do normal meshing, which means it has a kind of uniform, optimal element size. So if you double click or click on this and build all, so this is the, let me make this window a little bit bigger so you can probably see better. This is the element shape in COMSOL. Then you can go coarser. If you go coarser, the element size is going to be bigger, as you can see over here. Or you can go finer, and your elements are going to be smaller. So the finer your mesh is, the more elements you get, like this one, and that will mean that you're going to have a your simulation is going to take longer to solve. So there is this balance between accuracy and simulation runtime. For this one, it's not going to take too long. It's a very simple analysis, so I'm not going to be worrying about it. But when you have very complicated simulations, especially if it's multiphysics nonlinear, the more elements you have, yes, you're going to probably have more accurate results, but also you're going to have to spend a lot of time waiting for your simulation to end. So there should be a balance. We usually do a convergence analysis. We run the model for different types of meshing and element sizes and numbers of degrees of freedom. And when we see a very small difference or deviation between the models or results as a function of element size, that will determine that we're probably safe with the bigger element size and less simulation runtime for our case. In this case, I'm going to be a little bit safe. I'm going to keep it at finer, build all. So this is going to be the bar. I'm not very happy with this. Let's go make it extra fine. Maybe that's better. Okay, I'm going to solve this one, right? And again, there are more things we can do with meshing. I'm not going to go in detail of that now. We'll cover them later in the future examples because I want to make this video, I don't want to make this video too long. So after you're done with meshing, you can come into study, and then if that's all you want to do for the model, you can say compute, or you can click compute over here. And let me just expand this window so you will see what happens. So like I said, in the messages window, you see all the messages that COMSOL wants to give you. Every time I tried to mesh, COMSOL told me how many elements, domains, and boundary conditions or boundary elements were created. So one thing else you can do, if you want to have information about your mesh, is right click on the mesh tab and click statistics. Sorry. In statistics, when you do that and COMSOL finishes what it was doing, it gives you some information about how many elements were created or are present in your model, some information about the element quality and the element mesh volume, so you can study that and put in your reports. And you can do the same thing or similar thing after you're done with your study. So let's run this analysis. And what I want to do, I don't know how long, this is probably going to take very little time to complete, so I might not have enough time to show you exactly what's happening. So let's click compute and wait for COMSOL to finish this analysis. So it finished like in 5 seconds. If you look at the log window, this whole thing just happened in that 5 seconds. Again, if you're running a more complicated analysis, you will see these, it's going to take forever, or it's going to take some time, not forever. And in the progress window, you will see how much the simulation has progressed. And there will be a window if you're doing a nonlinear analysis specifically, you can see if your model is converging or not converging. So in the future examples, when we go through more complicated analysis, you will see those happening over here. So once you're done with that, COMSOL by default shows you some results, some colorful results. Let's zoom out of here. So it's showing me the stresses. What kind of stress is that? Let's take a look. So there is a tab here. If we click on the arrow and the volume, I see that it's showing me solid mechanics dash von Mises stress. So by default, COMSOL is showing me the von Mises stresses that, again, I can extend, I can extract and put in reports. For the sake of this simple example, I'm not going to go over this. This is something that we could do with hand calculations. So when we do more complicated examples, I'll go over deriving more advanced methods of deriving results from COMSOL. But I just want to show you how you can extract the displacement, for example, from this model. So if I go to results, I can click on the 3D plot group because this is a 3D analysis. And then I can click on volume because I want to show my analysis on the entire volume. So I can click on the volume here. Now by default, it's showing me the solid displacement. But this is the displacement unit. I just want to, let's say I want to see just the displacement in the y or in the z direction, in the length of the beam or the bar. So if I click on this red and green arrows, you see it says replace expression. I can click that and I have these options. I can click on each one, let's say solid mechanics. And then if I go down, I can find, say, displacement. And then in the displacement field, I have W. W is a displacement field in the Z component. So I can click this and replaces that. Or if I don't know, or if I know, if I don't want to go through all these click, click, click steps, if I know what I'm looking for, I can just type W and that would also work. I can change a unit as I want it to show me. So let's see what kind of displacement I get first. It shows the displacements are very, very small, like 10 to the minus 11. So it's not really that much. So I can change it, let's say, to the smallest nanometers. So if I click on that, this 10 to the minus 11 is probably going to be 10 to the minus 2. Well, it didn't do that anymore because the values are small or large enough in nanometers. So these are the same displacements, except they're shown in a different unit. And it shows in here that this is the nanometers. So I can click and I can show it in the XY window. I can show it in 3D view, or I can show it in the YZ window. One thing else I can do is I can try to show like displacement of this bar from its original shape. So once I'm clicking on this volume 1, I can come here to deformation under the 3D plot groups tab, and then go to deformation, and now you see that it was here, the original geometry, the original shape, but it has been expanded by probably 0.5 nanometers. I can change the names of these to make it more professional. So I can change it, say, to solid displacement, and I can say this is Z displacement, and it changes accordingly. And then you can basically take a picture of this, but that's not very professional for reporting. Again, I will go through more in-depth result extraction from COMSOL in post-processing when we have more advanced models and analysis. This one is a very simple thing that, again, we can do with hand calculation, so I'm not going to spend too much time in this video. So in this video, we went through the basics. What is the how does COMSOL look like, and how do you define well, create geometries, how do you mesh things, apply material properties, and run a simple simulation and see some of the results. In the next videos, we'll go over some more advanced analysis.